a system design interview, sometimes you ask to estimate the system, sometimes you ask to estimate system capacity or performance requirements. So back of the envelope estimation according to Chaplin Senior Fellow. Back of the envelope calculations are estimations you create using a combination of thought experiments and common performance numbers to get a good feel for which designs will meet your requirement. You need to have a good sense of scalability basics to effectively carry out back of the envelope estimation. The following concepts should be well understood. Power of 2, latency numbers every programmer should know, and availability numbers. Actually, I was looking into learning how to calculate the database size. This is good for system design, but I'm more interested in database. I think ByteByteGo has a YouTube video which does that. We'll go from the oldest. Mm, What happens when you type URL in the browser? What with this? Don't think so.
Would you say yes to a software development job outside India? Where
Back of the envelope map is a very useful tool in a system design toolbox. In this video, we'll go over how and when to use it, and share some tips on using it effectively. Let's dive right in. Experienced developer use back of the envelope map for quality check design. Its absolute accuracy is not important. Usually it is good enough to get within an order of magnitude or two of the actual numbers we are looking for. For example, the map says at our scale our web service needs to handle 1 million requests per second. Each web server could only handle about 10,000 requests per second. We learn two things quickly. One is DAU, or U, of the service we're designing for. For example, not everyone active on Twitter makes a post, so only a percentage does. How do we store? Not store password. Protection is a one-way function to store passwords. Here are the recommendations. The source is a password. Provide password is
Would you say yes to a software development job?
Today, we're diving into the world of computer memory and storage. Let's get started. First up, we have the fundamental duo, RAM and ROM. RAM, or random access memory, is a type of memory that stores data temporarily while the computer is running. It's fast and flexible, juggling all the programs we're running at any given moment. However, RAM is volatile, meaning it loses its stored data when the power is turned off. ROM, or read-only memory is a type of memory that retains data even when the power is off. It is non-volatile and used to store essential information like firmware and the BIOS that your computer needs to boot up. It's also worth and BIOS. Now let's high performance report, a quick journey through the world of computer memory and storage. If you like our videos, you may like our system design newsletter as well. It covers topics securely store password and SHA-1 as a one database based. This simple text generated salt, and the salt user logs in the user from the store in the database. Please subscribe if you that we use and then to add more Q&A. The team will contact what about the user contact important of the user. Follow socket with client. We should use behavior we want. The client is of discussion design. At scale, data modeling could significantly the important and ask if they have any. When building a highly scalable system, choosing the right database is often the single most important decision you'll ever make. You're fortunately enough to be able to task the challenge choosing the right database for a super fast growing business. Here are some key points to consider. We're talking about a database for a real growing business, where a bad choice would lead to extended downtime, customer impact, and even data loss. We're not picking something for a weekend project. This take is probably a bit controversial. Let's dive right in. First, are we positive that we need a different database? There's a compelling reason we started to look for an alternative, right? Is the existing database breaking at the seams? Maybe the P95 latency is through the roof. Maybe the working set is overflowing the available memory, and even the most basic requests need to go to disk and slow everything down. Whatever the issues are, make sure they are not easily solvable. Now let's read the database manual of our current database system, front to back, and then read it again. There could be a configuration knob or two that we can tweak to give us a bit more breathing room. This breathing room could come in handy because migrating a database could take a long time, usually much longer than we think. These knobs could come in the form of tuning the working set memory size, choosing a different compaction strategy, or even changing some garbage collection behavior. Databases are complex and highly tunable. Understand the architecture of a database. Know its limitations. Reach out to experts in the community. Describe our problems. People in the know can help, and often in surprising ways. Look for more untapped headroom. Maybe there are some fixes to our application architecture that will give us more breathing room. Can we put a cache in front of it and give us a few more months of runway? Can we add replica to upload some reload? Can we shard the database or partition the data in some way? Maybe the data is naturally siloed. Sharding is an acceptable solution. Bottom line is this: migrating live production database is risky and costly. We better be sure that there's no way to keep using the current database. Okay, we have exhausted all avenues for the current database. How do we go about choosing the next one? We developers are naturally drawn to new and shiny, like moths to a flame. When it comes to databases though, boring is good. We should prefer the ones that have been around for a long time and have been battle tested. Depending on the industry we're in, our posture could be a little different. Banking and finance is a lot more conservative, for example. Whatever it is, there should be a ready market of experienced administrators and developers for the database we are considering. Software engineering at scale is about trade-offs. When it comes to databases, it is even more true. Keep in mind there is no free lunch. Be wary of outrageous marketing claims. Infinite, effortless horizontal scalability comes with a hidden cost. Dig deep to find where that cost is hiding. Instead of reading the shiny brochure, go read the manual. There is usually a page called Limits. That page is a gem. The FAQ section is also very useful. These pages in the manual are where we learn the real limits of a new database, its design constraints, the fine prints, so to speak. The brochure promises infinite horizontal scalability. These are the places to fact-check those claims and define the catch. In our experience, the fancier the claims, the longer the disclaimers in the back. For example, many NoSQL databases support much higher scale than the trusty old relational databases. They often claim to support near linearly horizontal scalability. Now here are the common trade-offs that come with them. 1. They eliminate or limit transactional guarantees. 2. They severely limit data modeling flexibility. There are no questions. Welcome to another system design video. In this video, we design a proximity service. What is proximity service? This is a service that is commonly found as a backend component in an app like Yelp to find the best restaurants nearby, or in a mapping app to find the closest gas stations. Let's first understand the problem and establish a design scope. Different apps may have different requirements for the proximity service. In this video, we designed the service as part of the business review app like Yelp. This app has many features when it comes to searching for nearby businesses. It is not feasible to design all of them in this video. We'll narrow down the functional requirements to its core feature set. Here are what we came up with. 1. Given the user's location and a search radius as inputs, return all businesses within the search radius. 2. Business owners can add, delete, or update a business. These changes don't need to be appear in real time. It is okay for the changes to appear the next day. 3. Users of the app can view detailed information about a business. Next, it is important to discuss the non-functional requirements. Non-functional requirements place various constraints on design. Well, let's look at the high-level design. In this section, we'll look at API design, data schema. We'll then walk through the high-level design diagram. First up, let's take a look at the API design for this service. Here we use a RESTful API convention. This keeps things simple. Based on the functional requirements we discussed above, we have two broad API categories. first category is for searching nearby businesses. This is a single GET request that takes as input latitude and longitude of the user's location and an optional search radius. This API returns the business in an array of business objects along with the total count. 2 points to note here. First, we simplified the API for this short video, omitting pagination. In real life though, we should include pagination in the API design. Second, business objects in the API response contain just enough information to render the search result. It does not include enough information to render the detail page for the business. To render the business detail page, another API endpoint is needed. This brings us to the other API category. The second API category manages business objects. It includes corrupt endpoints to create, read, update for the service. There are two key database tables for this. First is the business table. This holds detailed information about nearby distribution member so far. Now that we discussed the schema, we should be able to do some backup envelope calculation on storage requirements. Now, what do we know so far? There are 200 million businesses. The business table, we estimate that all the details for a business should take no more than 10 kilobytes. On average, it would probably be closer to 1 kilobyte. So the business table should be in the low terabyte range. How about the table for nearby searchers? This table should hold the business ID, latitude, and longitude for each business. These are all 8 bytes each. That's about 200 million times 24 bytes, which is about longitude for in the low terabyte range. That all the details for a business should take no more than 10 kilobytes. On average, it would probably be closer to 1 kilobyte. So the business table should be in the low terabyte range. How about the table for nearby searchers? The low terabyte range. How about the table for nearby searchers? This table should hold the business ID, latitude, and longitude for each business. These are all 8 bytes each. That's about 200 million times 24 bytes, which is about 5 gigabytes. This tells us that this dataset for location search is tiny. When the database is this tiny, we have a lot of design options, including those that are purely in memory only. We're now at a point where we know enough to put together a rough high-level design diagram. This system, there are 2 parts, each mapped to an API category mentioned earlier. We call the first part location-based service, and the second part business service. Let's take a quick look at each component of this high-level design. First is the load balancer. Now designed, the load balancer distributes incoming traffic across 2 services based on API routes. As we will see later, both services are stateless. Deploying stateless services behind a load balancer is pretty common, and we will not go much deeper here. But note that in the real world, the company we work for might have other setups for distributing traffic to services. It could be Envoy in a Kubernetes cluster or API gateway on AWS. The exact details doesn't matter that much. Behind the load balancers are the 2 services mentioned earlier. The location-based service is a core part of the system. It finds nearby businesses for a given search radius and location quickly. The location-based service has a few interesting characteristics. First, it is read-heavy with no write requests at all. Second, the QPS is high. 5,000 QPS was the earlier estimate. Third, the service is stateless. It should be easy to scale horizontally. Next is the business service. Business service is the other service behind the load balancer. This service handles the correct requests for managing business objects. versions of the API is not high. Based on our functional requirements, the changes also don't need to take effect right away. This gives us a lot of flexibility on the design. For reads, though, QPS could be high during peak hours. Since this data doesn't change frequently, it will be a good candidate for caching if necessary. Now, more on caching later. Next in the high-level design diagram is the database cluster. We have not discussed what kind of database we will use. We'll visit that topic in detail. However, based on the access patterns and read-write query volume, you already know enough to take a crack at what database topologies to use. Let's summarize what we know so far. The services are read-heavy. The read QPS is much higher than the write QPS. The writes don't need to be immediate. The search data set is not very large at all. The business data set is a bit bigger. The search data set is not very large at all. The business data set is a bit bigger, and we might need to optimize it. We will revisit that in a bit. Based on these observations, using a database cluster primary-secondary setup seems to be a good starting point. Now, in this configuration, the primary database handles all the write requests, and the read replicas handle the heavy read requests. Data is saved to the primary database first, and then replicated to the replica. There will be some data inconsistency caused by replication delay. Since the changes to business don't need to be reflected in real time, the inconsistency is not a problem. At this point, we have a good idea of what the overall system looks like. Let's dive deeper into a few interesting areas. Let's discuss what database to use to power the location-based search. There is a class of databases called geospatial databases. It is optimized for storing and querying data in geometric space, like location data. Some examples of these databases are Redis GeoHash and Postgres with PostGIS extension. To understand at a high level how these databases work, we'll take a bit of a detour and discuss the common algorithms behind the geospatial index that powers these databases. This knowledge could help us choose the right solution for production environment. The most intuitive but inefficient way is to draw a circle and find all the businesses within the circle. Now, this pseudo SQL query shows us how we'll implement something like this in a database. The where clause looks a bit complicated, but it basically finds all the businesses that are within the bounding box specified in the where clause. The thing that jumps out is that this query is not efficient. It requires a table scan. With 200 million entries, it is slow. Now, how do we improve this? One idea is to build indexes on the longitude and latitude columns. Will this make it more efficient? The answer is, well, not by much. Let's see if we could spot the problem. Here we have two-dimensional data. The dataset returned for each dimension is huge. We could retrieve all businesses within a longitude range or a latitude range. But to fetch businesses within a search radius, we need to find the intersection of those ranges. This is inefficient because each dataset still contains a lot of data. Looking at it another way, the root problem with this approach is that the index can only improve the search speed in one of the two dimensions. Naturally, the follow-up question is this: can we map two-dimensional data into one dimension so we can build a single index on it? The answer is yes. There are two general approaches when it comes to geospatial indexing. The first approach is hash-based. Some examples are EvenGrid and GeoHash. The second approach is tree-based. These include Quadtree and Google S2. Even though the underlying implementations of these two broad approaches are different, the high-level idea is the same. They divide the map into smaller areas and build indexes for fast search. Let's explore the hash-based solutions first. One simple approach is to evenly divide the world into smaller grids. One grid could have many businesses, and each business belongs to one grid. This approach has one major issue. The distribution of businesses is uneven. There could be lots of businesses in downtown New York, for example, while in rural areas there could be very few businesses. Ideally, we want to use more granular grids for dense areas and larger grids for sparse ones. GeoHash is an improvement to the evenly divided grid. It works by reducing the two-dimensional location data into a one-dimensional string of letters and digits. Now, what does that really mean? Let's go over how GeoHash works at a high level. First, it divides the world into 4 quadrants along the prime meridian and the equator. For the location-based service, we're only interested in string, halves of the world. For example, in the current grid. But it is good to have a different set of deployment and operational constraints. For our design, we will focus on using GeoHash instead. Okay, so back to GeoHash. We want to use GeoHash as the geospatial GeoHash. We don't need a special geospatial database for that. The GeoHash column contains the GeoHash of the right precision for each business. Converting a location in latitude and longitude to a GeoHash is straightforward. There are plenty of libraries to handle that. 2 things we should discuss with this table schema. First, many businesses will share the same GeoHash. This means different business IDs within a GeoHash are stored in different database rows. And the GeoHash and business ID columns together form a compound key. With the compound key, it makes removal of a business from the table efficient. Second, as we discussed earlier, for our application, we're interested in GeoHash with precisions 4 to 6. They correspond to different search radii from 0.5 kilometers to about 20 kilometers. The GeoHash column in the table will all have a GeoHash precision of 6. We'll use the light operator in SQL to search for shorter prefix lengths. Now here's an example. With this query, we find everything that is within the GeoHash of 9Q8ZN. Next, let's talk about how to scale the geospatial index table. Do we actually need to scale beyond one database for this table? Well, let's do some quick math. For this table, each GeoHash is 6 characters long. And let's assume that the business ID is 64 bits, so that's 8 bytes. Optionally, we might also want to store latitude and longitude for each business, so that it is easy to calculate the distance of each business from the user. So let's add another 16 bytes to it. So each row is about 30 bytes. With 200 million businesses, the total table size is about 6 gigabytes. This is tiny for modern hardware. The entire dataset can easily fit in a single database server. However, our read QPS at 5000 is quite high. With peak time spikes, a single database might not have enough CPU or network bandwidth to handle all the read requests. But what are some of the ways we could spread the read load? There are 2 general approaches. We can add read replicas or we can shard the database. Sharding is more complicated. It requires sharding logic in the application layer. In our case, the entire dataset can fit in a single machine. There is no strong reason to shard. A better approach for us is to have a series of read replicas of the geospatial index table to help with the read load. This method is much easier to maintain than sharding. The last point we would like to touch on is caching. Do we need a caching layer in a design? It is not obvious if caching is a win. Our workload is read heavy, and the geospatial dataset is small. As we just discussed above, if read performance is the bottleneck, we can add read replicas to help. However, there's another dataset in our design. It is the business table. We estimated earlier that the dataset for the business table with 200 million businesses is in the terabyte range. For modern hardware, it is not that large. The dataset size is on the borderline where sharding might make sense. For this table, the update rate is slow and it is read heavy. We should be able to get away without sharding if we put a cache in front of it. This cache would take most of the read load of the frequently accessed businesses, and it should give the business table quite a bit of headroom to grow. Adding read replicas could also help with the read log. We have a lot of options for the business table. Our recommendation is to first ship it with a single database. As the product grows, and with the help of good monitoring, we can react to the growth and usage patterns and decide later on either to shard, add replicas, or add a cache in front of it. Now for this video, we'll omit the cache layer. Let's recap by tracing the life of a search request through our final design. Bob tries to find restaurants within 500 meters. The client sends the location and search radius to the load balancer. The load balancer forwards the request to the location-based service. Based on the location and the search radius, the service finds the geohash precision that matches the search request. 500 meters mapped to geohash length of 6. The service calculates the neighboring geohashes. There will be a total of 9 geohashes to query against the geospatial index table. The service sends a query to the database to fetch the business IDs and their lat-long pairs within those geohashes. The service uses the lat-long pairs to calculate the distance between the user and the businesses, rank them, and return the result to the client. Now that's it for the design of the proximity service. If you'd like to learn more about system design, check out our books and weekly newsletter. Please subscribe if you learned something new. Thank you so much. We'll see you next time. What do DynamoDB, Apache Cassandra, Discord, and Akamai CDN have in common? They all use consistent hashing. Now what is consistent hashing? Why do all the cool kids use it? In this video, we'll learn all about it. Let's dive right in. In a large-scale distributed system, data does not fit on a single server. They are distributed across many machines. This is called horizontal scaling. To build such a system with predictable performance, it is important to distribute the data evenly across those servers. A common method to distribute data as evenly as possible among servers is simple hashing. This is how it works. First, for each object, we hash its keys with a hashing function like MD5 or murmur hash. This maps the object key to a known range of numerical values. A good hashing function distributes the hashes evenly across the entire range. Second, we perform the modular operation on the hash against the number of servers. This determines which servers the object belongs to. As long as the number of servers stays the same, an object key will always map to the same server. Here's a concrete example. We have 4 servers with 8 string keys. With simple hashing, this is how we distribute the 8 string keys among the 4 servers. Now, this approach works well when the size of the cluster is fixed and the data distribution is even. But what happens when new servers get added to meet new demand, or when existing servers get removed? Back to our example, if server 1 goes down, the size of the cluster is now 3. Even though the hashes for the object keys stays the same, we are now applying the modular operation to a different set of n. In this case, it is now 3. The impact is pretty drastic. Most of the keys get redistributed. This affects almost all objects. It's not just the objects originally stored in the server that is now offline. This triggers a storm of misses and lots of objects to be moved. For situations where servers constantly come and go, this design is untenable. Consistent hashing is an effective technique to mitigate this issue. The goal of consistent hashing is this. We want almost all objects to stay assigned to the same server, even as the number of objects changes. Here is the core insight of consistent hashing. In addition to hashing the object keys like before, we also hash the server names. The objects and servers are hashed with the same hashing function to the same range of values. In our example, we have a range of x0 to xn. This range is called a hash space. Next, we connect both ends of the hash space to form a ring. This is a hash ring. Using a hashing function, we hash each server by its name or IP address, and place the server onto the ring. Here we place our 4 servers onto the ring. Next, we hash each object by its keys with the same hashing function. Unlike simple hashing where we perform a modular operation on the hash, here we use the hash directly to map the object key onto the ring. Here's what it will look like for our 4 objects. To locate the server for a particular object, we go clockwise from the location of the object key on the ring until a server is found. Continue with our example. Key 0 is on server 0 and key 1 is on server 1. Now let's take a look at what happens when we add a server. Here we insert a new server S4 to the left of S0 on the ring. Note that only K0 needs to be moved from S0 to S4. This is because S4 is the first server K0 encounters by going clockwise from K0's position on the ring. Keys K1, K2, and K3 are not affected. With simple hashing, when a new server is added, almost all the keys need to be remapped. With consistent hashing, adding a new server only requires redistribution of a fraction of the keys. Let's walk through a quick example of removing a server. When S1 is removed, only K1 needs to be remapped to S2. The rest of the keys are unaffected. Let's recap. What have we learned so far? 1. We map both servers and objects onto the hash ring using a uniformly distributed hash function. 2. To locate a server for an object, we go clockwise on the ring from the object's position until a server is found. Now let's consider a potential issue with this design. The distribution of the objects in the server on the ring is likely to be uneven. Conceptually, we pick n random points on the ring. We are very unlikely to get a perfect partition of the ring into equally sized segments. For example, if servers are mapped on the ring like this, most of the objects are stored in S2, with S1 and S3 storing no data. This problem gets worse if servers come and go frequently. In our example, even if the servers were originally evenly spaced, if S1 is removed, the segment for S2 is now twice as large as the ones for S0 and S3. Virtual nodes are used to fix this problem. The idea is to have each server appear at multiple locations on the ring. Each location is a virtual node representing a server. In this hash ring, we have 2 servers, with each having 3 virtual nodes. Instead of having S0 and S1, we now have S00, S01, and S02 to represent server 0, and S10, S11, and S12 to represent server 1 on the ring. With virtual nodes, each server handles multiple segments on the ring. In our example, the segments labeled S0 are managed by server 0, and those labeled S1 are handled by server 1. In real-world systems, the number of virtual nodes is much larger than 3. As the number of virtual nodes increases, the distribution of objects becomes more balanced. Having more virtual nodes means taking more space to store the metadata about the virtual nodes. This is a trade-off, and we can tune the number of virtual nodes to fit our system requirements. Let's see how consistent hashing is used in the real world. Some popular NoSQL databases like Amazon DynamoDB and Apache Cassandra use consistent hashing where it is used for data partitioning. It helps these databases minimize data movement during rebalancing. Content delivery networks like Akamai use consistent hashing to help distribute web contents evenly among the edge servers. Load balancers like Google Load Balancers use consistent hashing to distribute persistent connections evenly across backend servers. This limits the number of connections that need to be reestablished when a backend server goes down. That's it for consistent hashing. If you would like to learn more about system design, check out our books and weekly newsletters. To 1 kilobyte. into this later. Now that we discussed the schema, we should be able to do some back of the envelope calculation on storage requirements. Now, what do we know so far? There are 200 million businesses. For the business table, we estimate that all the details for
We are preparing a PostgreSQL database for production usage, and we need to estimate the storage size for this database. We are a team of developers with low expertise on database administration. So we are doing research, reading manuals, and using our general information technology knowledge to achieve this. We have actual data to migrate to this database and have some rough estimation of growth. For the sake of example, let's say we have estimation of growth of 50% per year. What is a general proper technique for doing good size estimations? We are estimating the storage usage by following rules. Topics where we need advice are marking with full text. Feedback on whole process is more than welcome. Estimate the size of each table, discover the actual size of each row. For fields of fixed size like bit in, char, we use sizes described in the documentation. Okay. So each type of database data type, these are the data types that are used to store the data. And if we use small int, it takes 2 bytes. That's 8 bits, which includes positive and negative. So if it's unsigned, I can store up to 64,000 values of rocks. So for most cases, big int is more than enough. So I'll be going with 8 bytes. Well, integer itself is about 20, wait, 100,000 million, about 2 billion. So that's 2 billion values. And 2 billion is, I think, enough. All the range of values is all the integer values from to inclusive. Mhm. The standard integer types store up to 4 billion values, including 0, and this will print negative numbers by default unless otherwise specified. finding it looks like. Yeah. Position rollover denoted by what's the small binary. So if we have big int, which is about 64, quite a lot. What's the storage size? Storage bytes. Int takes 4, big int takes 8, and Postgres takes big int takes 8. Decimal, variable, real, double, serial. Postgres is much more complicated to work with. I would say let's not do Postgres at all. Not worth it. Okay, small int is 2 bytes, big int is signed and signed. So if you don't use unsigned values, just negative values, pretty much double the maximum value you can use in that column. Just have to add unsigned flag. I showed you would create an int column using the column syntax. So you can do zero fill, and that would actually add additional zeros with the return values. Well, if you have invoices and all, this would be pretty amazing to do. But unless you need, yeah, I don't think we need to look at any point. Which control of the point equations do you choose to negative number? Nah, we don't need. And 4 billion is more than enough. How many domains? Register domains at the time of this writing. Yeah, using big int from the beginning actually is not a bad idea, but yeah, continue. The field with the dynamic size like text, we estimated the string length and used the function expected here text. Okay, we added 4 more bytes for OID. Uses intern OID, what is that? Basically gives you a built-in ID for every row. Oh, that's like primary ID. That's handy for tables where you don't have a primary key. Why? We don't need that. So yeah, based on this, we calculate the number of items we need, multiply the size of each row by the number of estimated rows, like how many rows you have. Do I need to consider any overhead here, like row or table metadata? Estimate the size of each table index. Don't know how to estimate this. Need advise your estimate size of transaction log. To advise your estimate size of the backup full and incremental. Don't know how this advise dash. Sum all the estimates for actual minimum size. Apply a factor of 1.5. The reversion group to the sum estimates 1, 2, and 4 for the minimum size after 1 year. Apply an overall factor of 1.2 to 1.4 to estimate 5 and 6 for a good safety margin. I know the rules got pretty extensive that if examples are necessary for better understanding. No, this is like very nicely written. Bruno Palacco. When you populate a sample database, example 10% of the size, in that case, you could use PG total related size to get the real size of each table, including indexes. There are a lot of questions. And input consider the heap tuple header data layout table for the metadata at the row level. Okay, the propriety is absolute for user tables. No longer have the default. Okay. Lot of data is live, yet frequently updated. Estimating that the size is harder because updates are equivalent to insert new version followed by delete old version, followed hopefully by reuse of unused space whenever possible. There is also the fill factor storage option for tables that come in play here. And there is a bloat at index level 2 for write heavy tables. It's not uncommon for an index to be several times bigger than its optimal size. Hmm. Hmm. But this is pretty cool. I can actually see. I just hope like how Postgres is all of this in one. Oh no, I really don't understand what is this. Skip. I had all of this data types in one page. It would have been much easier if MySQL had the same thing. Mhm, mhm, mhm. Mhm, Yes, right. A server with hundreds of databases, it can take minutes to calculate. What is the quickest method of calculating this? Just looking at the file system. Right. Do some data stored in the German file. Hmm.